Hi, let me tell you about another great Manning book, CUDA for Deep Learning, written by Elliot Arledge.
Large language models burn through staggering compute budgets. Training in days rather than weeks, or inference in milliseconds rather than seconds, often comes down to GPU efficiency. CUDA is the bridge between PyTorch's clean abstractions and the silicon that executes the work. PyTorch can make GPU acceleration feel wonderfully simple. Move the model to CUDA, run the code, and the network finds another gear. For many tasks, that is enough. But if a custom operation bottlenecks the pipeline, or an embedded system needs strict real-time inference, the framework may not give you enough control. CUDA is NVIDIA's programming model for code that runs on the GPU. PyTorch uses CUDA under the hood. This book teaches you to write low-level GPU code yourself, then optionally integrate it back into familiar frameworks. Most of the time, custom CUDA is unnecessary. cuBLAS, cuDNN, and framework backends cover common cases well. It becomes valuable when the workload falls outside those paths. New attention patterns, million-token contexts, robotics latency limits, fused operations, custom quantization, or novel architectures. The common thread is control over operations, hardware, memory, latency, and throughput. CUDA begins with two cooperating worlds. The host is the CPU and system RAM, where the main program controls the application. The device is the GPU and its VRAM, where thousands of simpler workers execute parallel arithmetic. CPUs favor complex logic. GPUs favor throughput across many data elements. Because host and device memory are separate, CUDA programs move data explicitly, allocate GPU memory, copy input to the device, launch the kernel, and copy results back. A kernel is a GPU function launched across many threads. You write logic for one thread, working on one piece of data. CUDA launches thousands of copies, each with its own index. The key pattern is same operation, different data. Activations, convolutions, attention scores, and gradient updates all expose work that can run at once. ReLU on a million values is not one long loop. It is a million small jobs waiting for threads. Parallel work still has to respect memory. Global memory is large but slow relative to on-chip storage. L2 cache buffers device-wide traffic. Shared memory and L1 are smaller and faster within each streaming multiprocessor. Registers are tiny and immediate. Fast CUDA keeps data in fast tiers as long as possible. Matrix multiplication shows why this matters. A naive kernel may reread the same inputs from global memory. An optimized version caches reused values in shared memory and cuts traffic dramatically. Sometimes the fastest algorithm has the most GPU-friendly memory pattern, not the fewest arithmetic operations. GPUs are not automatic wins. Tiny problems, low arithmetic intensity, and irregular control flow can lose to CPU execution because transfer cost, launch overhead, or warp divergence overwhelms the benefit. Knowing when parallelism does not help is part of the job. Deep learning is well suited to CUDA because it is built from repeated operations over large arrays, matrix multiplication, nonlinearities, convolutions, gradients, and attention dot products. Some are independent, others require reductions. Either way, deep learning produces many output elements that can be computed at once. CUDA began in 2007, and AlexNet in 2012 showed that neural networks could be designed around GPU parallelism. The first CUDA kernels will often be slower than PyTorch. That is expected. Frameworks call optimized libraries, while a naive kernel may read from slow memory and miss obvious efficiencies. CUDA is the starting point, not the destination. The stack then builds memory and compute optimization, tensor cores, kernel fusion, quantization, and distributed computing. Each layer attacks a bottleneck, and the improvements compound into higher throughput, better memory efficiency, lower training cost, and lower latency. Single GPU skill comes first. Multi-GPU work adds a communication hierarchy, where links inside a machine are faster than links between machines. Inefficiencies multiply as devices are added. So the single GPU lessons carry directly into distributed systems. CUDA is an ecosystem. CUDA C++, cuBLAS, cuDNN, cuBLAS, Thrust, the toolkit, drivers, and more. This book focuses on CUDA C++ because the low-level model teaches performance reasoning even when higher-level libraries execute the work. To begin, you need an NVIDIA GPU, NVCC, drivers checked with NVIDIA SMI, Python, Basic C, PyTorch familiarity, and enough linear algebra for matrix multiplication. The roadmap moves from first kernels to neural network building blocks, full training pipelines, transformer inference, profiling and optimization, tensor cores, flash attention, quantization, and multi-GPU systems. The essential requirement is curiosity and persistence. Once a custom kernel delivers its first real speedup, CUDA stops being hidden machinery and becomes a tool you can shape.
Get this book at Manning.com